All right. So for my classes, they require me to do like a project which I research at the end, and then this semester they also all wanted presentations. So I have three presentations, and I might as well present them here, so that you may learn something maybe. Uh, so this one is going to be the one that requires the least physics knowledge because it's about math, and it's for my math methods class. It's about constructible regular polygons, CHUD. That's me. I the only thing I changed in this presentation from when I gave it like 2 months ago uh, was that I changed my full name to just be Chud. Anyway, we're going to talk about constructible regular polygons. Okay, that doesn't work. Guess we're going with the mouse. Okay, so geometric constructions. What are geometric constructions? Also known as Euclidean or straight edge and compass constructions. This guy over here is Euclid. Uh, did a lot of geometry, wrote the elements. Um, Important math fella. Anyway, for geometric constructions, basically we have these three rules, three accepted rules. Technically, he had five, but one of them was wrong and one of them was redundant. So, really, we only use three. The first one is that straight lines can be made from a point to a point. Second is that straight lines can extend infinitely, and also that circles can be made from line segments. You know, if you have a point and you have a distance, you can use that to make a circle. Basically, straight edge, compass. You can make straight lines, you can use a compass. Technically, if you want to be pedantic, a pair of compasses, but not important. Uh, so we can sort of formalize this by making these constructible sets Pn, Ln, and Cn of points, lines, and circles. And as you can see here, ln plus 1 means that you have a line where you have 2 points, and each of these points is part of the set of points. The circle is you have a point, and then you have a distance where all of these are points. And then the more complicated one is points, where if you have a point on two distinct lines, a point on two distinct circles, or a point on a line and a circle, as in their intersections, then you can add that as a new point. Anyway, so the question is, which regular polygons are constructible? And so I have here an example of a square being constructed. So you start with, you always start with technically two arbitrary points, but for all of this, people just use 0 and 1. And it's in the complex plane. We'll get to that later. Anyway, so you have these 2 points. We'll call this 0 and 1, right? So you can open up a circle of any radius, really, around one of these points. Then use that circle, or at this circle, right? You take this point and this point, you consider this to be the center, this to be the radius, make a circle. And then that's how you get this one. And then you do the same thing for this one. Now, where these two intersect, you can make 2 more points. And these points are perpendicular to this first line. And then you can take this radius to go along this line, and then once you hit that, you get another point. And then there's a bunch of different ways where you can finish up this square. Point is, you can make a square. You can also make a triangle. You can also make a pentagon. That's harder. A hexagon isn't like too hard because you can combine triangles. Heptagon, that's the first problem. It has 7 sides. Now, the ancient Greeks did not know if you could make a heptagon. They just couldn't figure it out. That didn't necessarily mean that they had a way to prove that it was impossible. It actually is impossible. We'll talk about it. But first, we have to talk about fields and extensions. A field is a group, which is a group is a set with operations on it, and then it has to fulfill some rules. Basically, a field is a group in which addition, subtraction, multiplication, and division, excluding 0, all work under the rules of a group, which I'm not going to get into. But basically, they follow some requirements. So some examples are rational numbers, real numbers, and complex numbers. Now, a field extension adjoins an element to a field to get a larger field. And technically, it doesn't need to be larger, but that's called a not proper extension. And really all of these, like all the research in this field is about proper extensions, because they actually do something. Because you get a larger field. So for example here, probably the easiest one is this one, where you have the real numbers, and you're adjoining I, which is the complex unit, sort of. And so you end up with a plus ib, where a and b are real numbers. And so this is just gives you the complex field. So this extension specifically gives you the complex field. This extension doesn't. You're taking the rational numbers, as in anything that can be expressed as a fraction, and you're adjoining the square root of 2 to it. The square root of 2 is not rational, which means you can't express it as a fraction, and you end up with a plus root 2b, where a and b are rational numbers. And so this is a bigger field than just rational numbers, compared to something like adjoining 2 to the rational numbers. Well, 2 is already in the rational numbers, so this isn't really extensions. This isn't really an extension. And the same thing with adjoining the square root of 2 to the real numbers. Not an extension, or not a proper extension. It's an extension, but it doesn't matter, no one cares. And so we have to talk about the algebra of these extensions, and these extensions are described in two ways. You have algebraic and transcendental. An algebraic extension essentially just means that you have a non-zero polynomial in which, using that, whatever you're adjoining, you get 0. So yeah, non-zero polynomial such that p of k is 0 and the coefficients are in the original field. So for example here, this is an algebraic field, and transcendental fields specifically are defined as like, it's just not an algebraic field. So for example here, adjoining pi to the rational numbers is a transcendental extension, because even though you're adjoining something that isn't in the original field, it's actually impossible to make a polynomial with rational coefficients of which pi is a root. Same with like e, whatever, unimportant. Again, we're going to be looking at algebraic extensions. About extensions, we have to talk about their degree, and for that we can talk about the minimal polynomial, which is the unique monic polynomial of smallest degree, in which whatever you're adjoining is a root. So monic means that the leading coefficient is 1, and so that's basically just a polynomial of smallest degree with a leading coefficient of 1. I have here some examples. So if you're joining I to the real numbers, I squared is -1, -1 plus 1 is 0. And since it's squared, then the degree is 2. Here, again, sort of same thing. And then if you adjoin these two elements, the minimal polynomial is a degree 4, which means this extension is degree 4. So now we can go back to constructions, and there is such a thing called a Pythagorean extension, which is where you have this original field and you're adjoining an element that is the square root of a squared plus b squared. You'll notice that's like the Pythagorean theorem. That's kind of why it's called that, where a squared plus b squared is c squared, but if you take the square root of both sides, then you get c. And what you get is this thing called the Pythagorean closure, which is the union of all constructible points. And importantly, I'm not proving anything here. I'm not proving anything in these presentations, because this was just like brief presentations, take some questions, yada yada. So a point is constructible if and only if it exists in the Pythagorean closure. And this is very important. I can give you a little bit of intuition as to how, right? So if you take this first circle as having radius 1, then you have this, these are 1 and 1, it's a 45, 45, 90 triangle, so this is going to be the square root of 2. So the square root of 2 is constructible, as you can see here. If you go 1, 1, square root of 2. Now you can use this first one to make another circle, and then you have the square root of 2 plus 1, and then you can do whatever that results. And so you can do this forever for whatever square roots you'd like, and it will be constructible. So the degree of a Pythagorean extension is always 2 or 1. It's 2 if it's a unique, or it's 2 if you get a bigger element, it's 1 if it's already in there. And so you get this thing called a degree tower, where if you keep adjoining elements forever, you end up with higher and higher degree. So if you start here with like square root of 2, if you adjoin that, then degree 2. If you do 3, it's degree 2. 4, square root of 4 is 2, and 2 is already in the rational numbers, So that one has degree 1. Anyway, the point is, a point is in the Pythagorean closure if it is an extension of degree 2 to the n. And that means that the minimal polynomial of the extension has to be degree 2 to the n. So let's look back at a regular heptagon. So as I said, this has to do with the complex plane, because the complex plane, conveniently has 2 directions, x and y, or real, imaginary, whatever you want to call it. But point is, we're starting from 0 and 1. And so the way that you would construct something in the complex plane, especially if you want specific sides, you can take this from the Euler formula, and 2 to the pi, or 2 pi I, is going to be a full circle, right? And if you divide it by 7, then what you're saying is you're breaking 7 points along the circle. And so if we can construct any of these points, then we can construct the regular heptagon. And we know that because if we can use this point 1 and 0 to make whatever this point is, then we can just use this point that we made and 0 and follow the same process to get this point, and then so on. So really, as long as we show that any of these points are possible to make, then we know that the heptagon is possible to make. So what that means is that we have this polynomial that we need to solve. Z, which is a complex number to the power of 7, needs to equal 1. So we can rearrange that, and this actually can be factored. And if you remember, monic polynomials are the smallest degree, which means that actually the smallest polynomial where this is possible is 6. And since the degree is 6, which is not 2 to the power of n, a regular heptagon is impossible to construct. Now that's pretty cool, but it gets cooler, in my opinion. We have to talk about Gauss. Maybe you know him. Important guy. And he's 19 years old. He's thinking about the heptadecagon, as in 17 sides. And it hits him that cosine of 2 pi over 17 is equal to this. I have no clue how he ended up with this, but since you can see everything here is like under square roots, that means that it's constructible. And we can show that by our roots of unity method, right? Where if you break it into 17 pieces, z to the 17 minus 1 is 0, you can factor out z minus 1, and you end up with z to the 16 whatever. And 16 is 2 to the n, because it's 2 to the 4, right? 2 to the 1 is 2, 2 to the 2 is 4, 2 to the 3 is 8, and then 2 to the 4 is 16. So since it is, then it's constructible. So if we want to know which regular polygons are constructible, we need to know which polynomials are reducible, as in which you can do this kind of thing to. And so for that, we have the Eisenstein criterion, which was a student of Gauss's. I'm not going to read any of this, who cares? Point is, you follow this down the line, and you end up with the Gauss-Wanzel theorem, which is saying that an n-gon is constructible if and only if n is 2 to the k times these p's for integer k and distinct Fermat primes pi. Fermat primes are of the form 2 to the 2 to the n plus 1, and we only know of 5, although technically we don't know if these are the only 5, there might be more. But what you'll notice is that for a prime p here, this is just some lemma that's related to this. For some prime p, for a prime p, the polynomial p minus 1 is reducible. And so that cancels out this one here, which naturally leaves you with this 2 to the 2 to the n form, which is how you can put this here, where you have 2 to the n, and then these are all going to be 2 to the 2 to the n at some point. Anyway, just because Gauss proved that he knew it was possible to construct doesn't mean that he knew how to do it. That came later. What year was this? 1796. And then in 1803 actually came the first construction. And interestingly enough, we have constructions for all of these Fermat primes. Yeah. If you feel like it, go ahead, Google some instructions on how to do it, and follow along. This was my attempt. It took like an hour. You'll notice it's not actually a regular heptadecagon, because a regular would mean all of these points are equally apart, which they're not. As it turns out, it's extremely, extremely precise to do, and very, very hard. But really, all it is following instructions. It's just very precise. Anyway, I thought that was cool. And this is just something I learned about in geometry like a long time ago. And I thought that this research project would finally give me a chance to sort of look into why, how, and everything else. Anyway, yeah, that's the math project. Probably the most understandable one for a non-science audience. We're going to move on to the next one now. How's it going, guys? Chud is back. Today... Oh, fuck, I guess in the video it's all going to be combined. Anyway, I'm moving on to the second presentation, the one that I did for my Quantum 2 class. And it's comparing macro and microscopic superconductivity theories. This one's going to be a little harder to follow along for the non-physics audience, but I'll try. So superconductivity was found in 1911 by H.K. Onus when he was studying mercury. And so what superconductivity is when your electrical resistance falls to zero, quote unquote to zero. Technically, he didn't observe it falling to zero. I think he found it falling to like 10 to the minus 4, minus 5, what, unimportant. But basically, all of a sudden, resistance goes away, and electrons move around and whatnot, and it's cool. But we didn't know how it worked for a while. And so, like, one of the first major... Okay, major isn't exactly right, because the London equations came before. That was like the 1930s or something. But like a good phenomenological model came in 1950 with GL theory, or Ginzburg-Landau. This guy on the top, that's Ginzburg. Guy on the bottom, Landau. The mouse is... Oh, the mouse is visible. Cool. Anyway, this is a snippet from the Wikipedia page I found kind of interesting. It's literally the first line of GL theory. It says, in physics, Ginzburg-Landau theory, often called Landau-Ginzburg theory. I just thought that was kind of funny. Anyway, so what is it? What is this theory? It's a thermodynamic approach using a complex order parameter, which is this psi here. It's here, and it's here. And essentially, Landau had this theory of second-order phase transitions, and Ginzburg went, okay, well, what if we make it work for, like, electrical stuff, which is what the complex part is. Usually, if something... Okay, I don't want to say that. That's not right. But electricity can be described with complex numbers because you have... like phase and amplitude, and complex numbers can do that. Anyway, so what is this? I don't remember if I go over these parts in the presentation. I gave this like a month and a half ago. But basically, this is going to be the free energy of the superconductor. This is the free energy of the normal state. So superconducting, this is all of the superconductor, but this is of the superconducting phase, this is of the normal phase. These are just constants, and then the complex order parameter here. This has to do with the gradient in the field, and then this is the magnetic field. Okay, so spontaneous symmetry breaking is what's important here. And I said it was a phenomenological model, which means they sort of observed what happened and then built it up from there, as opposed to deriving it in some way. So ignoring fields, which is these two terms, Ignoring fields, if we subtract the normal phase, we can get this equation for the free energy, where alpha and beta are functions of temperature. And so here's a little graph of it. And what's interesting is when alpha is more than 0, then you get this parabola. And when alpha is less than 0, then you get this shape. I mean, it's just a fourth order polynomial, but whatever. Anyway, beta is always positive, because if it wasn't positive, then it would be increasingly negative arbitrarily. And so what you get here is a spontaneous, as in instant, symmetry breaking, as in the symmetry here immediately chooses either this minimum or this minimum. In physics, you're looking for energy levels and vacuum states. Or, well, I mean, not necessarily. But basically, you have this vacuum state, and then all of a sudden, as A passes negative, your vacuum state changes. This is the new lowest level. And it's a function of temperature. Superconductivity, temperature related. The whole reason why this happens is because of temperature. And it's at a critical temperature, Tc. So alpha behaves like Tc, where as soon as your T is equal to Tc, this is 0. And then you, on either side of Tc, you either go into this regime or into this regime. And so that's why they followed this. They were like, we don't exactly know why this works, but this is like what our physics is demonstrating, and this equation works for that. So a couple years later, BCS theory, or Bardeen-Cooper-Schrieffer, Schrieffer? I think it's Schrieffer. Anyway, Bardeen-Cooper-Schrieffer, they won the Nobel Prize for this. Oh, there's an extra space here. I never noticed. Oh, shit. Oh, well. Anyway, so these three guys, they came up with a quantum mechanical approach to redefine the vacuum state. But specifically, okay, technically they did it in 57. But this guy over here, Nikolai Bogolyubov, helped it along in 1958. And here, as you'll notice, Bogolyubov transformations, it's a very important part of the theory. So quantum mechanical approach here. Okay, so they're taking this equation to be the Hamiltonian. It's commonly called the reduced Hamiltonian, and there's two parts here. This part is... Okay, so first off, what is a Hamiltonian? A Hamiltonian is like a linear algebra type thing, right? Is there like a pointer? Oh, awesome. So this is the Hamiltonian. Okay, and technically, can I undo? I've never used these before. Oh, wait. Okay, so these are operators. And then these are, I mean, not really vectors, but they're sets of vectors. This is mimicking this, right, which is from linear algebra. I talked about this a little bit in my math video. You have this matrix, and then lambda is going to be your eigenvector, and then v is going to be your eigenvalue. Okay, I kind of wrote it backwards. It's traditionally lambda is the eigenvalue, and then v is the vector. Okay, I'm going to redraw it. Perfect, perfect. Okay, so AV equals LV. Right, and so what this does is you have this matrix A, and you have these vectors and eigenvalues. When this matrix acts upon this vector for any there's is a whole. How do I how do I skip as many steps as possible while still explaining it? Basically, we're solving this equation for lambda. Lambda gives us, in terms of this, right, we have psi, which are going to be our sets of eigenvectors, or in this case, for quantum physics, they're going to be our wave functions. H is our Hamiltonian, and then E is going to give us our energies. In physics, you're always looking for energies. I hope you just believe me on how that works. Anyway, so how does this work? So this part has to do with the energy of non-interacting electrons. A and A dagger are the creation and annihilation operators. K, negative K, L, and negative L are momentums. So when this is placed like this, right, you're going to slap a wave function on the end of these. And so you get like AK acting on psi, and then you get A negative K acting on psi, you get A negative L dagger acting on psi, you get A L dagger acting on psi. And all of those are going to give you things. They're all going to give terms. The terms here correspond to non-interacting electrons. The terms here correspond to interacting electrons, where you can see that you are taking a pair of electrons with opposite momentum, which you have an electron with k momentum, and then you have an electron with negative k momentum, so their total momentum is 0. You are destroying them, and then you are creating two new electrons with opposite momentum again. And then this is the pairing. Actually, it's not called a pairing function. Unimportant. This is a potential function. This potential function, since this is all linear algebra, this potential function looks like a matrix. And it's got like a bunch of elements, yada, yada, yada. Importantly, this matrix is 0 everywhere except along the diagonal. So only when k equals L does this like do anything. Oh, this is such a chore to erase. Okay. So basically you have these two parts. You have non-interacting electrons, you have interacting electrons. And there's this transformation, this Bogoliubov transformation, which takes these operators, AK, A negative K, A dagger K, whatever, and it redefines them in terms of alpha and beta. So these are two new creation and annihilation operators. And so you can do a little bit of math, and you can find that in terms of alpha and beta and these U and K functions, you can get AK and A negative K. Okay. How do I put this away? I want to just continue. Okay, whatever. Okay, anyway, you do math. You rewrite this as this, and you have this delta here, which is the pairing strength. The pairing strength is just this here. You end up with the quasi-particle energy EK. Again, everything is looking for energy. Quasi-particles are those of the redefined vacuum state. And their energy is this initial electron kinetic energy plus this pairing strength. Is there really no way to get rid of this eraser? How do I... Oh, shit. Oh, cool, it's gone. Perfect. Anyway. Okay. And then you end up here with the quantum mechanical approach. So now let's do like a quick little comparison. Above the critical temperature, where T is greater than Tc, this potential function is 0. It's defined that way. Because this function is only defined to exist near the Fermi surface, and so above this critical temperature, the function is just 0. which means that the pairing strength is also 0. Now, if we look at the phenomenological model, or the macroscopic, this is microscopic, this is macroscopic. When Tc, right here, right, we're saying T is greater than Tc, this is positive, which means alpha is positive, and that means you get this 0 here for the complex order parameter. Below the critical temperature, now this is no longer 0, and you have a pairing strength. And the same thing here, where now your vacuum changes. It's not 0, it's going to be this new below 0 thing. So the question is, how do you get, since these two theories describe the same effect but from different directions, there has to be some way to connect them. And so we can start from Helmholtz free energy. And that's, again, this is thermodynamics. I'm not explaining any of this. Take a thermodynamics class. So you start from Helmholtz free energy, and then for a normal state, not a superconducting state, normal state, right, here, the pairing strength is 0. Superconducting, it's not 0. So for a normal state, this delta is 0, which means that Ek, this one, right, if this is 0, then it's just the square root of this epsilon squared, which is just epsilon. So you end up with this. You can plug a bunch of things in, and then this is just an identity. So up here is going to be the superconducting phase, and here is going to be the normal phase. So we can expand this energy about delta, because delta we're taking is 0, so we can expand it about 0, make this approximation, plug it back into the energy, lots of numbers. Anyway, you get this expansion here. Now, if we pair terms together, you end up with this, right? You end up with a as a function of t times delta squared plus b over 2 as a function, b as a function of t over 2. Really a bunch of like weird errors in this. Anyway, so you have this a delta squared, b delta to the 4th. Now if we allow delta to vary in space, and we add a term to preserve gauge invariance, which is to say we are conserving charge, then we end up with this additional element, and then we can add that on. So if we look at the initial Ginzburg-Landau theory, ignoring magnetic fields, right, because there's an additional b term over here, you can see how this a, which we found as a function of t times this pairing strength squared, is analogous to this alpha times complex order parameter squared. And the same thing with these two, and then the same thing with these two. You can move around constants. You'll find out that they work the same. I think that's really cool. This was first shown by this other guy, Goryakov, because GL was very popular in the Soviet place. Soviet physics was good and cool and awesome. And then BCS was all done by Americans. So these were two things that were done by competing countries. Actually, this wasn't Cold War yet, so I guess they didn't care. But basically, GL wasn't really used much in the Western world compared to in Russia. And after Goryakov released his paper comparing these two, albeit using green functions, which I didn't do. Green functions are hard, annoying, didn't want to do it. I thought just this approach from thermodynamics was more straightforward. That made more sense to me. And what that did is it made GL both more popular and more credible, and it showed how the constants in GL could be defined through like the microscopic, from the quantum mechanical approach, basically. And so, it shows that even though superconductivity, this is the original graph. Oh look, it was 10 to the minus 5. Even though superconductivity is sudden and unexpected, it's not a mistake. Because you have this like steady decline, and then you hit this temperature and it drops. That's so cool. But we know that since macroscopic theory describes how it works, microscopic theory describes how it works, and that they're proportional near the critical temperature, which is to say at the critical temperature, they look the same, they act the same. It's so cool. Superconductivity, it's cool, it works. Physics is cool. It works. Okay, that's the end of my presentation. It's cool. Superconductivity is cool. I thought it would be interesting to sort of study these two approaches, and so that's what I did. Cool. Done. All right, last one. And now, this is on the same day. I'm recording this right after. This one I did for my E&M class. I wanted to look at modes in a toroidal cavity. This is like 5 words that will make sense to no one, but that's okay. We'll talk about it. So first, TE and TM modes. TE... Never mind. What are modes? Modes are when you have a conductor, you have an electric field that travels through it. Oh, it's time to bring up the fucking pen again. So let's say you have like a square, or not a square, but like a rectangular conductor, right? And you have an electric field traveling this way. You will have these like sinusoidal modes. Basically, you only have certain allowed equations for specific fields under specific conditions in a conductor. They're defined by the Maxwell equations here. You combine these into the wave equation. Take a differential equations class, you'll cover that one. And specifically, the modes are determined by boundary conditions. So TM means transverse B field is 0, whereas TE means transverse E field. So that's magnetic, that's electric. If you're wondering why B is magnetic field, that's a good question. It's actually H. H is the magnetic field. I hope that makes more sense. Anyway, and then it's got these boundary conditions. Who cares? Not very important. Basically, let's talk about modes in a cylinder first. So a cylinder has this coordinate system. I didn't need to explain this to any physicists, they all knew it. But I'll cover it now. So coordinate systems. Traditionally, right, this is your Cartesian coordinate system. You have your x, your y, and your z. And it's like, oh, you go 3 this way, and then you go 2 this way, and then you go 1 this way, and you can find your coordinate. The cylindrical coordinate system is different. The cylindrical coordinate system, conveniently, I have a picture right here, right? You still have 3 terms because they need to be, you need to describe 3 dimensions. It's just that there are phi and z. So z is still going to be this vertical line. R is going, okay, rho, whatever. Rho is going to be how far away you are from the center, and phi is going to be how much, like, your angle is. So you can still describe any point in 3D space with these 3 numbers. And so the question would be, why would you ever use a different system? And that's because it makes solving equations easier. So if we solve the wave equation, this one, by separating in this r theta z, it's like the variables are used interchangeably. This one's rho phi z, this one's r theta z. It doesn't really matter. I guess technically r theta z is more of a math thing, whereas rho phi z is more of a physics thing, but who cares? Anyway, you solve the wave equation by separating, and you end up with this solution. Oh wow, that's a terrible line. It covers half the equation. It covers half the equation, where these are just sinusoidal functions as a function of, well, I mean, z, of course, but you also have the length of whatever the cylinder you're looking at is. And this n is just going to be numbers, right? Specifically integers. So you have like n equals 1, n equals 2, n equals 3. Those are all going to be modes. And importantly, right, oh, I should talk about standing waves. Standing waves are so cool. Anyway, if you have For example, like n equals 1, it might be something like this. N equals 2, it'll be something like this. N equals 3, it'll be something like that. The point is, these define how the waves work in the thing. And then over here, J is going to be the spherical Bessel function. Not spherical, just the Bessel function, regular Bessel function. And so we find the modes by replacing this arbitrary psi, right? This is just solving the equation. If we're looking to solve the modes, we replace them with either EZ or BZ, right? And transverse electric, transverse magnetic means transverse, so along this cylinder. That's what we're looking for. So, and also we add time dependence, but that's easy. We don't really need to cover that. Anyway, if you replace those, you end up with these solutions here for your modes. I'm not going to read them out. Who cares? These are your frequencies. And then XMA is going to be... I don't want to talk about Bessel functions. XMA is going to be the alpha function of the M Bessel function of X. You find these constants by plugging in the same way you would for any differential equation. The only difference here is that this is going to be the derivative. Moving on. So let's consider a toroid, since I want to look at modes in a toroidal cavity, as opposed to just a cylindrical one. So this is now our coordinate system, compared to the other one. Here, it's a little more complicated, as you'll notice. It's got both trig and hyperbolic trig. So again, we have to describe motion in 3D space somehow. The way that this does it is phi is going to be, I believe, around this way. Theta, I think, is still this way. See, I had to explain this one because not everyone's familiar with it. You don't pull up the toroidal coordinate system often. I had to look up what it was to explain it, and I have since forgotten it. And then this zeta, or xi, this xi has something to do with like the length between something, I don't really remember. Anyway, the major question is, what even is transverse here? Whereas here, in a cylindrical system, it's easy to tell what's transverse. It's just along the cylinder, right? You have the z direction. In the square, you can really pick whichever direction. It can be x, y, or z, depending on the orientation of your thing. Here, there isn't really a transverse direction. It's always curving, right? Because for a cavity, we're letting like the electric fields move through it. And since it's always curving, we don't really even have a transverse coordinate. Even worse, the metric coefficients are coupled together, or they couple the fields together. Whereas in a cylinder, these are metric coefficients, they come from these. Not these are the toroidal ones, but these come from the cylindrical one. These separate nicely, right? You'll notice this is 1, that's easy. This is 1, that's easy. This is r. It's not easy, but for a given r, it's easy enough. And since hz is the one that we want to look for, these are going to decouple nicely. So you can get a separable solution. But these don't. These modes end up coupled together. The way you find these metric constants, they're all going to have phi, xi, and theta in them, which means they don't separate. So these, the quote-unquote, where's my mouse? The quote-unquote TM modes, right, if we're calling this the transverse, it also has components of electric field. And if we go back, TM, right, B field 0, boundary E is 0. These need to be 0 at the boundary. They're not. So we have a problem. And the same thing with these. So how do you solve it? Well, as physicists, we could just approximate a solution for a toroid, right? Because these don't decouple nicely, we have to find a different solution. Now, I did actually find a math solution that used like half-integer Legendre polynomials and like some other shit, and I did not want to read into what the hell any of that meant, so I didn't. So we're going to just look at a perturbation theory approach. And we're going to approximate a solution for a toroid based on what we know about cylinders. So first, we make this thing called a large aspect ratio approximation. That's saying that, if this is our toroid, right? That's saying that this cross-section is going to be a lot smaller than this radius, right? So that sort of allows us to make it a ring. Is that what it is? Yeah, the cross-section radius is much smaller than the distance to the toroid center. That allows us to treat the curvature like a perturbation, right? Since it's basically a very, very long ring with a small radius, at every like instantaneous point, you get slices of a cylinder. And we treat the curvature as a perturbation. That changes this dz, right? So the change in the z, which is what we're going to call the transverse direction, it gives us this sort of change with d phi. This means that our transverse metric factor is now this, right over here. And since we're making this approximation that the radius is a lot smaller, we're taking r to be very big. And if we take r to be very big, you have 1 over something big, right? That's going to go to 0, which means this term goes away, and our metric factor is now just constant. So we can separate solutions. Yippee! You'll notice this is the exact same solution as before, just with this term changed. And now we just take the standard perturbative approach, which is to say we know something about, where's the mouse? We know something about E0. We want to make the next approximation of E1. And E0 here is going to be the standard cylindrical solution. So we know the standard cylindrical solution. This here is going to be the perturbation in the Lagrangian, or not the Lagrangian, in the Lagrange operator, right? Because that's this one. Basically, we're taking the solution we get using the regular Lagrange operator. We're taking the regular solution from the Lagrange operator. We're taking this sort of little bonus approximation, and then we are taking the inner product with these solutions, and then divide it by the frequencies. That's going to be our constants, taken a sum of however many you want, and then there you go. That's going to be your first order solution. If you want the next order solution, you do the exact same thing, but now you have E2, and then you do, I mean, it's more complicated than this one. I didn't want to write it out, but you do some sort of solution regarding E1. So in one way, this is interesting. In another way, it's kind of boring. Because one thing I've sort of always wondered is, why does E&M always have the exact same examples? It's always like, oh, you have a cylinder, you have a box, you have two concentric spheres. And as it turns out, it's because of the geometry. Once you like leave the basic geometries which have nice symmetries, you end up with impossible to separate solutions, and the only way to do them is to just approximate and like do a perturbative approach, which is like, cool, you do it once, but it's for everything. So that's kind of why all of the examples are always the exact same. It's because once you leave those examples, there's no like extra pedagogical value, I guess. You just hit everything with the same perturbative approach, or approximate everything. Anyway, yeah, that one's cool. Still, I kind of liked it. You get to look at toroidal coordinate systems. How often do you get to do that? Anyway, cool. Those are all my physics presentations. See ya. Goodbye. Maybe I'll talk about standing waves later. Probably won't. Okay, bye bye.